All right, this is section 7.3. So we made it through part of this before the spring break and all the craziness happened, but I'm going to pretend like we didn't. So this section is on perfect numbers and Mersenne primes. And so what we want to do is we want to define what a perfect number is, and this leads to a connection with a type of prime number known as a Mersenne number, known as a Mersenne prime. There's sort of a interconnection between the two, and that's what we want to establish and look at some examples. So basically, let me just say that by way of an intro. So turns out that where perfect numbers originally came from was the definition of sigma. So the original definition of sigma of n, remember this was the sum of the divisors, positive divisors, I'll just say divisors, leads to perfect numbers, which are connected to Mersenne primes, which is sort of one of the most common types of prime numbers that get found. To Mersenne primes. So first definition. This was the definition we saw before we left for break. So positive integer is perfect if the sum of the positive divisors is twice the number. So an integer n in z plus, so positive is perfect if the sum of the divisors, I'm just going to say of divisors, but positive divisors, equals twice the number. In other words, sigma of n is 2n. Sometimes this is stated as the sum of the proper divisors equals the number, which means you don't get to count the number itself, but either which way it's the same. So for example, if you check n equals 6, we find sigma of 6. The divisors are 1, 2, 3, and 6 itself. That gives us 12, which is 2 times 6. So 6 is perfect. So these are sort of interesting, like I said, because they connect to Mersenne primes. So this question comes up of like, how can we find these? Right? If they're interesting, how do we find these? Well, finding perfect numbers. So the first thing I want to say is also something we said in class is that, and this is sort of fairly interesting fact, is all the perfect numbers that have ever been found have been even, and there have been a finite number of them. So there are two big unknowns just off the bat. So unknown A is, are there infinitely many? That's unknown. And B is, are there any odd ones? In other words, all the ones that are found of even have been even. All found ones are even. But nobody's proved that there couldn't be any odd ones. So the first fact that we have is sort of interesting. It makes a connection between perfect numbers, or what it means to be perfect, and a certain form of those numbers. So first is this theorem. It says that the integer n, positive integer, z plus, is perfect if and only if it has a certain form. So that form is if n is 2 to the m minus 1 times 2 to the m minus 1. Careful with the minuses there, where m is an integer, positive integer with m greater than or equal to 2, and 2 to the m minus 1 itself is prime. So what this means, just before we look at an example and give a proof, or half a proof, is that when you're looking for perfect numbers, what you really have to look for is things of the form 2 to the m minus 1, which are prime, right? So what this means is finding perfect numbers then means finding m greater than or equal to 2 with 2 to the m minus 1, or 2 to the m minus 1 prime. Right? So what you could do, right, in theory, is you could just start checking m's, right? I mean, this is not a feasible approach, but we could check m equals 2, 3, 4, 5, etc. And then when 2 to the m minus 1 is prime, right, if that happens, then we get a perfect, right? Then n equals 2 to the m minus 1 times that prime that we just found. Right, this is not feasible because, of course, you need to check if 2 to the m minus 1 itself is prime. So there's a little bit of work there, right? But for an example, when m equals 2, it works. All right, so if you look at 2 to the m minus 1, that's 2 to the 2 minus 1, that's 3, that's prime. So, conclusion of the theorem is that n equals 2 to the m minus 1, which is 1, times 2 to the m minus 1. Right? That turns out to be 2 times 3, hold on, yep, sorry, that's 6, which is perfect. So that works out nicely, right? So I'm going to prove half of this. The backward direction is pretty straightforward. The forward direction is sort of a bit of a pain, so I'm going to omit it. It's fairly lengthy. It's in the book, so you can check if you want, but here's the backward direction. So here's the proof of the backward direction. So what we're going to do is we're going to assume you have an m greater than or equal to 2 with 2 to the m minus 1 prime. So we assume that m is an integer greater than or equal to 2, and that 2 to the m minus 1 itself is prime. So notice that 2 to the m minus 1 is odd because 2 to the m is even. If we take the GCD of 2 to the m minus 1 and this guy 2 to the m minus 1, that'll be 1. Because the first one is power of 2, the only divisors are basically powers of 2, and the second one is odd, so the GCD is 1. So this is convenient because then when we take sigma of the product, remember the thing that we're trying to prove is perfect is the product of these two. So if we take sigma of the product, we can use the multiplicativity of sigma, right? So that if I take sigma of, well, let's do it this way. Let's say if we assign n to be 2 to the m minus 1, 2 to the m minus 1. This is the thing that we claim is perfect. Let's put that we claim n is perfect. So let's look at it, right? Sigma of n is sigma of that product. And this is equal to sigma of 2 to the m minus 1, sigma of 2 to the m minus 1. And this right here, this is by the fact that they're multiplicative. Right, remember that means that you can split it up when the GCD is 1, which it is in this case as we just showed. Right? So now let's look at each of these individually. Right? So look at sigma of 2 to the m minus 1. Right? So we're assuming that 2 to the m minus 1 is prime. That's one of the assumptions of the proof. That means the divisors are one in itself. So sigma of 2 to the m minus 1 is 1 plus 2 to the m minus 1, which is 2 to the m. That's the first thing to look at. So the second thing is to look at the 2 to the m minus 1, right? So look at sigma of 2 to the m minus 1, right? So we have a rule for powers of primes, which says that sigma of p to the k is the fraction p to the k plus 1 minus 1 over p minus 1. So that tells us that sigma of 2 to the m minus 1 is 2 to the m minus 1 over 2 minus 1, which is 2 to the m minus 1. So we know both of those sigmas, so let's look what happens when we multiply them together. So let's look at the product. Right, sigma of n is sigma of 2 to the m minus 1, sigma of 2 to the m minus 1. So this is back from this fact right here. That's just recopying that right over there. Right. And so we just calculate these two. So the first of these is 2 to the m minus 1. The second of these we just calculated, what we calculated first is 2 to the m. Right. So if we look at this, we can factor a 2 out of the second one. And these two together, these are just n written sort of in reverse order right here. So what this means is we've got 2n and we're good. QED. That's the backwards direction. Like I said, the forward direction is significantly longer and omitted. So again, you can check in the book if you're interested in seeing that. So what this does is this sort of punts the question, right? It's like, okay, so if finding perfect numbers means finding 2 to the m minus 1s that are prime, how do we know when 2 to the m minus 1 is prime? So the question has been, let's say, punted to or changed to the following. When is 2 to the m minus 1 prime? So that we can sort of say something partial about, right? So theorem. So we can say, for example, that if 2 to the m minus 1 is prime, this is sort of the wrong direction, but it's helpful, then so is m. This is actually not hard to prove. It'll fit into the corner of the screen right now. So suppose we're going to do it by the contrapositive. If m is not prime, so if m is a b, then if you take 2 to the m minus 1, this is 2 to the a b minus 1. Actually, this is not going to fit right here. Hold on, let me do this on the other side because it'll be sort of crammed in. Yes, let me rewrite this over here. This is 2 to the m minus 1 is 2 to the a b minus 1. So this, what this is this is a giant FOIL mess, right? So this is 2 to the a minus 1 times 2 to the a times b minus 1 plus 2 to the a times b minus 2. And this sort of goes down and down and down and down until we get 2 to the a times 1 plus 2 to the a times 0, which is 2 to the 0, which is 1. Right? And that's the end. So this multiplication is not obvious. It's just a question of foiling this out. And or if you like, foil is really the wrong word. It's like distributing it out and seeing. So this tells us that if we want 2 to the m minus 1 to be prime, then m better be. Which kind of helps. Now notice that the reverse of this theorem is false before we go forward. So note the reverse of the theorem is false. In other words, we can have m prime, but 2 to the m minus 1 not prime. So for example, if m is 11, that's prime. 2 to the m minus 1 is 2 to the 11 minus 1. That's 2047. And that's 23 times 89. So it doesn't work both ways. But the key thing to keep in mind is that this fact up here is that right here. So we only need to check m's that are prime. So this is the situation then. At least do a new definition. So just to summarize, finding perfect numbers is equivalent to finding prime p with 2 to the p minus 1 also prime. This leads to two definitions. This is where the Mersenne primes comes up. So first definition is the mth Mersenne number is just 2 to the m minus 1. So for example, the fourth Mersenne number is 2 to the 4 minus 1, which is 15. Notice that's not prime, no big deal. So next definition, so if p is prime, because it has to be for the next statement, and 2 to the p minus 1 is prime, then 2 to the p minus 1 is a Mersenne prime. These are some of the most common primes found because they're sort of easy to look for in the sense that there's a little more structure about them. Like they have to have this form. So rather than just sort of randomly fishing around at numbers when you don't know what you're looking for, this like sort of gives a good target, right? So at the end of the day, we get the following correspondence. It's not perfect, but just to clarify, p being prime is implied by 2 to the p minus 1 being prime, which is if and only if 2 to the p minus 1 times 2 to the p minus 1 is perfect. So just to see the correspondence, p equals 5. That's prime. That goes with 2 to the p minus 1, which is 31, which is prime, which corresponds to 2 to the 5 minus 1 times 2 to the 5 minus 1. That value is 496, and that's perfect. We can see that because sigma of 496, if you calculate it, this is not screamingly obvious, is 992, which is 2 times 496. So again, this implication right here, the leftwards implication, let me target this. This guy is not perfect, and well, no pun intended, but like that's not in the sense that like if we start with a prime on the left, you don't necessarily get this whole thing, but that's sort of built into the calculation in a way. So then the final question is then, of course, like, okay, so if you start with a prime p and you want to know if 2 to the p minus 1 is prime, how can you figure it out? So lastly, right, if we start with a prime p, how can we check if 2 to the p minus 1 is prime? because it could be just like, well, let's just try all the divisors, right? But that's not realistic, right? This is a big number typically, and so that could take a long time, right? So checking all divisors is lengthy. So there's a nice theorem that goes with this. And I'm not going to prove this theorem. The proof is not particularly long, but it relies upon a lemma back from the Euclidean algorithm, and the lemma is really long and computational. So, and it's not obvious, right? So if I just stated the lemma, it sort of wouldn't really help. It would sort of leave you in the dark, and it's much better in this case to do some examples. So what it says is the following, right? It says if p is an odd prime, what it does is it tells you about divisors of 2 to the p minus 1. So then any divisors of 2 to the p minus 1 must have the form 2kp minus 1 for k in the positive integers. So what this means is, when you're checking, right, when you want to check if 2 to the p minus 1 is prime, right, all you have to do, and it could still be lengthy if the number's big, is check multiples of not check multiples, but rather check expressions of the form 2kp minus 1 for k equals 1, 2, 3, ... And it turns out actually to be a little easier than this, in the sense that, well, we'll see. Let's look at a couple of examples here. So 2 examples. So remember the p equals 11. We saw this guy earlier, right? So let's consider this 2 to the 11 minus 1. This was 2047. What this theorem says is that any divisors of this must have a certain form. So any divisors must have the form 2kp, which is 11 plus 1. So this is 22k plus 1 for k equals 1, 2, 3, ... Now notice when we look at those, right, when k equals 1, we get 22, or we get 23. When k equals 2, we get 45. And when k is 3, we get higher. So we can stop there, right? So we stop there because if you look at the square root of 2047, right, this is approximately 45.24. So what this means is if there's a divisor bigger than this, it has a co-divisor that's less than this, right? So if 2047 had a divisor greater than this, then it would have a divisor less than this. Let's say a co-divisor. So these are the only 2 things we need to check, right? So we check, and if we check 2047 and we divide it by 23, we get 89, and we're done. It's not prime. So second example, consider p equals 13. Right? So then we look at, in this case, 2 to the 13 minus 1, which is 8191. So if we want to know this is prime, the only divisors must have the form of 2k13 plus 1, which is 26k plus 1 for k equals 1, 2, 3, dot, dot, dot. So if we check these, right, so if we notice, let's say, the square root of 8191, this is approximately 90.5. So that's where we can stop, right? So we only need to check 27 and 53 and 79, and none work. So it's prime. So it meaning 8191, right there. That guy's prime. In other words, when we say none work, when you divide 8191 by these, there's a remainder. It doesn't divide easily, right? Now, as a closing note, which I'll just put over here on the left-hand side, just because it fits, is we didn't actually need to check 27. Because 27 itself is divisible by 3 and 9, and those are not of the right form. Right, 3 divides 27, 9 divides 27. So in other words, if 27 did work, so would those. But they don't have the correct form, right? But they're not of the form 26k plus 1. And that's the end.